Hi, I'm Olivia, everyone's favorite math teacher, and in this video we're going to be talking about average rate of change, secants, tangents, and why this led to the creation of calculus. So here we have our definition for average rate of change and secant. And if this looks familiar, it's because the average rate of change is the slope. And this is just our slope formula written in function notation. So we're talking about using a function, any function, and then using an interval on that function. Therefore, we know that we're defined wherever we're going to be looking at this. And then instead of using x and y, we're talking about the domain and the range. Otherwise, it's the exact same thing. And then for the secant, we're talking about the line where you're just going through the 2 points on that same interval. And then this is simply the equation for a line in point slope form. If you've never seen that before, don't worry about it. It's pretty simple, and if you're used to using y-intercept form, this converts over pretty quickly once you plug your values in. Now, we're going to go ahead and look at exactly how this works with a graph, and you're going to see that, yeah, it's pretty standard stuff, and it's something that you're used to seeing. So this function comes to us courtesy of Galileo. In about 1590, he verified the acceleration due to gravity on falling bodies. For the purposes of this, down is the positive direction, okay? Now, in doing this, I just want to make it clear that the y-axis is graphing position and the x-axis is graphing time, okay? So the average rate of change is the velocity of the object. So in order to figure out how fast the object is falling, you need to figure out, or you would need to figure out, and he needed to figure out, the average rate of change on the graph. So, he would basically check to see how long it took an object to fall from various distances. He would plot those points and then figure out the average rate of change, right? And that's actually not too hard as long as you have multiple points. In fact, go ahead and do that. We've got a couple of questions up here. Feel free, pause the video, give it a try. How'd you do? So if you're a real go-getter, you might have tried that last one. And you might have found that there's a problem there, right? So let's go ahead and look at what exactly is going on here. Because when you do the first one, we say, what's the average velocity on the interval for 4 seconds and 5 seconds? Now, I'm just going to kind of estimate where these are, and it doesn't really matter. So we'll just say that, 0, we'll go with 1, 2, 3, 4, 5. Now, that's probably off. Doesn't really matter, right? And then we'll go with 6. Yeah, that's probably on my graph. 6, okay? So 4 would be here, okay? 5 would be here, and then 6 would be, we'll call it here, right? Okay, so when we find the average velocity on 4 to 5, we're finding the secant line right here, okay? And we find the slope of that secant line. And, we showed that a moment ago, right? And then when we find the average velocity on 5 to 6, we find the secant line here, okay? A little bit steeper, and we find the velocity here. Both of those require 2 points. But letter C is a little bit different. It's not asking for the average. It's asking for the velocity exactly at this point, and only at that point. And this is the problem, because I'm not asking for the secant. This is where I'm asking for the tangent, that one that we haven't defined yet. And there's actually a good reason we haven't defined it yet. Because under geometry and under algebra, there's not actually a good, strong definition for the tangent line to a curve. And that's because under classic geometry, you don't really deal with curves. You deal with circles, but not your standard curves, like not your function curves, right? So they didn't really have to come up with one. And then under geometry or under algebra, it doesn't really work because we're talking about needing to find a slope at a point. And the problem is, to find a slope, you need 2 points. But a tangent, kind of what it is, kind of the idea of what it is that it's a line that touches the curve at only 1 point, right? So it's a line that intersects our curve at only 1 point. And that also kind of is a problem when we're talking about curves, because if you have a curve that kind of does something like this, and you talk about a tangent at this point, well, if we have a tangent line, it's going to intersect here. So we really mean like locally tangent, and that also causes problems. So it just becomes a whole issue, right? And that's kind of basically, like I was saying earlier, I was saying that, we're going to talk about why calculus had to be invented. And this is basically why calculus had to be invented, is because we ran into problems like this all of the time. These related rates where we needed to know what was happening here. And we couldn't actually answer that question. We could approximate it, but we couldn't answer that question exactly at that point. And unfortunately, this wasn't a new problem. This problem actually dates back as far as like 400 BC. There was a philosopher named Zeno of Elea. He was a guy who might have existed, probably existed. We know of his existence mostly through the writings of Aristotle, who basically set this guy up as kind of a straw man argument to be all like, hey, this guy made these arguments that like motion doesn't exist, and here's his paradox. However, mathematically, the paradoxes he presented, at least a few of them, did ring true because they presented a problem where we knew a thing existed, but we couldn't calculate it in this way. And this is exactly that kind of a situation. You drop an object from the top of, in this case, the Leaning Tower of Pisa, and the object is falling constantly, and the speed is constantly increasing. At no point does the object just stop moving because you're looking at it, but yet I can't tell you what its speed is exactly at this point. I can approximate it. I can tell you what the speed probably should be, but I can't actually tell you confidently, mathematically, algebraically, exactly what that speed should be right there. Um, and that's a problem, right? And for Zeno, the way that he described it was like this. He said that an arrow in flight at any given moment occupies the space that it is in. So in that moment, because it is occupying that space, at that moment, it is at rest. And that's kind of the idea here, because we don't have a duration. And you have to remember, speed, velocity, is change in distance over change in time. And in a very instant, there's not a change in time. So by that definition, we can't find that velocity, right? And so therefore, yeah, we have a problem, and that was recognized back in 400 BC. We couldn't solve it then because we didn't have algebra. We invented algebra. We still couldn't solve it. So we invented calculus. Now, we did have ways of approximating this. So it wasn't like we said, oh, well, we can't do it, we're done. And I'm going to show you how we did that. And we did it using secants, okay? And the way we did that was, we have two methods. We can either average secants that we know to get an approximation, or we can reduce our interval until it's very close to here, and then say we're close enough. Like, basically, we're in the ballpark, we're good enough. It's like using the approximation of pi instead of pi itself. Okay, which is something that we do all the time because it's really hard to find pi on a ruler, for example, right? Same thing with things like the square root of 2. Squares exist. Every single diagonal on a square involves the square root of 2, so it's kind of hard to find that. So, we have to approximate things. And that's effectively what we did for a really long time, but mathematically, that's very unsatisfying. And like I said, because of that, we invented calculus. Now, let me demonstrate how, before we got calculus, we can solve that. And to do that, we're going to go to Desmos. So we're going to go ahead and show how to approximate a tangent using averaging secants and also using a decreasing interval. So we have those secants that we found earlier, and I'm going to go ahead and draw them in. And as you can see, those are honestly pretty close. And when you look at the actual numbers, the ones that you calculated earlier, I hope, you can also see that they're pretty darn close. So when we average these, our answer is probably also going to be pretty close. Hopefully everybody remembers how to do the average. All you do, add the two numbers up, divide by 2, see what we get. So we go 44.1 plus 53.9 divided by 2, and we get 49. So what we're saying is our speed at this point at 5 seconds was 49, and then it would have been meters per second. So let's see another possible option here, which would be, what if we decrease our interval and we get closer and closer and closer to this 5 seconds here. Now, I've got it set up to where we can do that. So I have S of 5, and then over here I've got A. And all we're going to do is we're going to change this A so that we can get closer and closer and closer. So if we set this at 6, you'll see that we have 53.9. That's exactly the average velocity that we got for that interval. Now, let's go ahead and just cut that in half. So we'll say 5.5. And you can see that, okay, we're getting a little bit closer. We're getting closer to that 49 that we kind of expected. Okay, well, yeah, that's pretty good. What if we go a little bit closer? Let's say we'll cut it in half again. So we'll go to 5.25. Okay. We're getting even closer. We're getting closer down to that 49. Okay, well, let's go a little bit closer. Let's go to 5.1. Hey, 49.49. Let's go to 5.01. Oops, too many decimals. 49.049. Let's put another 0 in there. So, as you can see, yeah, as we approach that 5, we seem to be getting pretty darn close to 49. That seems like a pretty good number to land on. So I hope that review of secants, average rate of change, and tangents helped out. And remember, if you have any questions, feel free to drop into the comments or join us on Discord. In the next video, we're finally going to start working on actual calculus.